The purpose of this video is simply to help you get from structures like this that you might have drawn and figure out from that what hybridization is involved. Now, I'm not going to get into what the hybridization actually is, but just to allow you to get from a picture to figure out the hybridization. And then I'll show you in a couple of cases what some models look like that would have this hybridization. So we're going to start with two electron groups on the central atom. And there's a couple of ways that could look. In your Lewis structure, it might look like this, or it could look like this. And again, we're only looking at the central atom in each of these cases to figure out the geometry. So this counts as an electron group and this does, or it could be a single and a triple bond. In either case, two electron groups are going to try to repel each other and get as far away from each other as they can. And that means the electron geometry is going to be linear in both of these cases, and the hybridization can be counted like this. 1, 2 is the number of bonds we need to make, so the hybridization will be 1, 2 orbitals will be involved. So the hybridization for all molecules on the central atom that have two electron groups attached is sp hybridization. And the molecule might look something like this. Here's our central atom, and the other two will be bonded 180 degrees from it. The electron geometry is linear, so is the molecular geometry. The molecular geometry actually takes into account the atoms that are attached, and it will also be linear for both of these. All right, so if we extend this to molecules that have 3 electron groups, again on the central atom, that's the only one we're looking at, it could look like this in your structure, or like this. So basically, if you have the incorrect Lewis structure, there's no way you're going to be able to make some conclusions about it. 3 electron groups are going to try to repel each other as well, and they're going to try to get as far away from each other as they can, and it's going to look something like this arrangement. 3 electron groups, 3 electron groups. In this case, I would have an atom attached here at this position. Here, this position might represent a lone pair. Either way, they're still going to repel each other and have a trigonal planar electron geometry, which means they're going to try to get 120 degrees apart from each other. And the hybridization is 1, 2, 3, 1, 2, 3, SPP. 1, 2, 3, and that's written as SP2. So both of these are going to be using in the structure sp2 hybridized orbitals, even though actually by shape name this molecule is trigonal planar, because all 3 would have atoms attached in all 3 of these positions. But in this case, the molecular geometry would be bent because there's only 2 atoms attached, and because they aren't in a straight line, we call it a bent structure. So different molecule geometries, but all of this is true for both of them. 4 electron groups, we can look at those similarly. 4 electron groups on the central atom, they also try to get as far away from each other as they can, and that is a tetrahedral structure. So it looks something like this, in which case the atoms try to get about 109 degrees from each other. I mean, the exact angle is not important, just that you recognize when something's, linear or not linear, 120 or something close to that is fine. So you don't need to worry about having exact bond angles. The hybridization, again, is going to be based on this 4-electron group count. Let's write the ways that that could look. It could look like a central atom, of course, with 4 bonds. It could be 3 bonds and a lone pair, or it could, in fact, be 2 bonds and 2 lone pairs. So a mistake that I will commonly see is students will call this a linear molecule. This is not a linear molecule. It can't be. What's true of all these, let's go ahead and do the hybridization. The hybridization is 1, 2, 3, 4. In every case, there's 4 electron groups. The hybridization is S, P, P, P. 1, 2, 3, 4. sp3 hybridized orbitals are involved in each of these geometries. Now, they don't have the same molecular geometry. This one here is a tetrahedral molecule. When one of the bonds is missing or a lone pair is involved, it looks like this. So we have a central atom here, and this is a lone pair. The molecule is trigonal pyramidal. It's a trigonal pyramid molecule. Okay, and if you were to see this model, it's not sitting flat like a trigonal planar does. You've got good pictures of these in your textbook. I guess the point I want to make sure we really make here is even though you might draw it on paper like this, it's most certainly not a linear molecule because it's trying to do its tetrahedral thing. So the lone pairs are here. I'm holding on to those. And the geometry of the molecule, central atom, 2 atoms attached, this is not linear. This is called a bent structure because these lone pairs are taking up space and causing repulsion, so the bond angle here is not 180 degrees. It's much closer to 109. So what these have in common are 4 electron groups. Their electron geometries are all the same. Their hybridizations are all the same, but they are in fact different molecular geometries. And then really, you know, we got lots more possibilities if there are 5. I just want to hit on if there are 5 electron groups, they try to make this trigonal bipyramid structure. Okay, which of course you can see what that looks like in 3 dimensions, but mainly I want to talk about the hybridization. It could of course look like this. 1, 2, 3, 4, 5. So if you start with an S, add P's, once you have added 3 P's, you're out of P's, so you start adding D's. 1, 2, 3, 4, 5, the hybridization is sp3d. And of course there's a number of ways that can happen. These could then start to become lone pairs, and then we get some different geometries to come out of that. But no matter what, if there are 5 groups, this is the hybridization. And likewise, if there are 6 electron groups, they're going to try to have an octahedral geometry, which is like a bunch of 90-degree angles. Would look like this. And of course, some of these could be lone pairs, and we could get some different geometries. But no matter what the makeup is here, whether they're single bonds or lone pairs, if you need hybridized orbitals to make up 6 bonds, count them 6. We have 3 P's, we can start adding D's, that's 5 electron groups, this will be the 6th one, so the hybridization is sp3d2. Okay, that's just a quick and easy way to get from here to here. Doesn't really explain hybridization, but it'll help you figure out what they should be in each of these cases.